Yeah, so for you guys who can handle the 4 year college in the US, including a part-time job, like including athletes, right? You're doing so many things at the same time and also get a degree. You guys are heroes. That's I didn't experience that. If I were like at your age, I don't know if I can handle this. So much.
You don't have a choice. You just have to.
I know you don't have a choice.
Too deep.
Yeah, since I know you guys can handle, that's why I'm giving you so many assignments. Since I know you guys are so good.
Setting up a resume.
Yeah, it's common, very common, right? High stress for the STEM majors.
Next semester, bro.
Next semester?
Yeah.
Okay, guys. I haven't plugged in yet. We still have, I think, 2 tutorials to go, but I know I won't let you work on it by yourself. It's a little bit unrealistic to let you guys figure things out by yourself. So I'm making these tutorials very easy to finish. And I'm still giving you in-class assignments so you can still learn something from the lectures instead of falling to sleep. And you can see tutorial 7, I'm going to teach, we're going to talk about SD cards and SPI communication. You know, and on Wednesday, we will have another tutorial I haven't got it done yet. That will be the audio playback because some students are working on a project similar to that. So you need to know how the low pass filters work, how the SD card spooling data out to the monitor, all things like that. So you know, every semester I made some changes to my syllabus. You know, a few years ago, I was thinking after I have taught a class for several times, it's going to be super simple. I just show up in the class and teach, and after that, I can just do whatever I want. But it's not a case. Every semester, I want to add something new to it since I learn new things from, you know, attending conferences and doing other things. It's been so stressful for like 8 or 9 years. I just couldn't teach all the old things, which are, you know, considered obsolete. It's not good for you guys. I don't feel excited about that. So, tutorial number 7, I just got it done 5 minutes before class started. So much work. Here is a tutorial, and you have a in-class exercise. Anyone doesn't have it? Before we get started, let's take a look at the final results so we know the goals. Okay, there are 2 demo videos. All right, don't get scared. The solution is provided to you guys. I'm not letting you guys code up everything by yourself. So let's take a look at the first demo. What we are going to expect in this task.
For tutorial 7, task 3, first start party. And I'm gonna initialize the SD card and then.
Yeah, you have to initialize the SD card first. It may not be super necessary for this library because I'm still exploring all the features of the library, but you know, doesn't hurt anything. So press the lowercase I on the keyboard to initialize the SD card and get everything set up.
Do a write. So I'm gonna.
So it's asking as a user to press any key to start recording of audio. But for task 2, did I record anything? Oh, I think I did. So I whistled.
Start whistling to it.
Wait.
So press start whistling.
Sorry, I put a wrong tutorial. I put the tutorial at the wrong place. So actually, I'm trying to play task 2. I'm going to swap the location of the 2 videos. So I'm trying to do this first, right?
Right. This is a demonstration for task 2, tutorial 7. It's about data acquisition and SD card write and read. So first, start party here, and I already saved the session. So first I have to initialize the SD card by pressing I on the keyboard, and then I have 3 different modes. The first mode I want to test is mode 0. If I press number 0 on the keyboard, it will write the current page number to the page or block,
Just writing counts.
which means there will be 512, the same number being written on the same page. Okay, so let's try it. Okay, the writing is success. So I'm going to press any key to start. I'm going to press S to start spooling the data to a file. And so it's asking me to do this. And so go to logging. And then all sessions, go to browse. I'll just save it on desktop. I'll name the file as data1.csv.
CSV file.
Apply. And then now you can start spooling your data over here. So I'm gonna press any random key on the keyboard. So now it's page 0, page 1, page 2, page 3, and
How's
0
the
are
numbers?
512.
0 to
The same
128.
number on each page. Okay, it's actually being read from the SD card, which means I already rolled these numbers into the SD card for 128 pages. And there's no way that I can wait until it finishes. So I'm gonna just press any key, random key on the keyboard to stop it. And they have to close this session in order to have the file shows up. Okay, so I have to refresh my desktop to display this guy. I'm gonna double click this file, and you can see all these numbers are being stored over here. Okay, yeah, let's see if there are 512. So here, and the last 0 shows at 513, I think. It should be 513. Okay, it's exactly 5.
So the reason that the last 0 is at 513 is because the first number started at 2, the row 2, right? So eventually there will be 512 bytes. And the reason for that is when you are dealing with SD card, you are writing or reading block by block. Just keep that in mind. So you are not actually doing byte by byte. You are doing block by block. And each block, or it's called a page on other online resources, each block has 512 bytes. Okay, so basically you are throwing 512 bytes to the SD card, or you are reading 512 bytes or a block or a page to your buffer at the same time. Just keeping that in mind. Okay.
13. Right, so this demonstration is successful. I'm gonna close this guy. And I'm gonna do it again. Open PuTTY again, and I will test mode 1 this time.
So mode 0, you can already see that we roll constant numbers. At page 0, we just read number 0 to the whole page, right? Just constant, just 0. The same number to the whole page. And how many zeros are in the page? 512, right? And, right, 512. And for the program, I'm doing 128 pages or blocks. So basically it's gonna write all zeros to that to page 0 or to block 0. And then until 127, right? 127 to page 127 or the 128th block. You know what I mean? But it's gonna take forever. You can tell it takes a long time. So for case number 1, what I did is I created a sine wave in array in my code, and I directly write that period of sine wave into the SD card. I'm doing that for multiple periods. So I read all these periods into the SD card first, and then I read from the SD card and plot it. So just instead of constants, I'm doing sine waves. Okay, let's verify the writing and reading operations of the SD card.
I'm gonna try to initialize this again, and I'm gonna press number 1 on the keyboard this time.
It's mode 1.
And then I will do spooling and right click.
Okay, keep in mind that, so after I press mode 1, right, it took about like half second or something. And then it shows write block success. So which means the writing is done. So as you can tell, it's pretty fast. But the thing is, you don't have a lot of data to be written into the SD card, so it makes sense. I just like few hundreds of bytes. You are not expecting like a few seconds. That would be ridiculous, right? You're expecting, sending or receiving video files a lot of times to the SD card. So after this shows up, all the writing is done, okay? And then I press S to lock, to save the data into a file, and also spool the data to the serial monitor so you can visualize the data being read from the SD card. Okay.
Settings.
This is what I'm doing right now to set up the file.
Login,
so you can save all the files
sessions, browse,
into the
and save the data as
CSV.csv.
data2.csv. All right, I'm gonna press any random key on the keyboard to try to spool the data, which is actually a sine wave. It's a pre-written sine wave. If you look at the code, you can find out what that is. So the sine wave being stored in the file. Okay, I'm gonna do it. You can see it's changing. I don't need that many. I'll just stop it. Right, and then I'm gonna close this guy, and I'll refresh. Okay, it shows up, and I will just plot this guy. Right, I don't have to plot everything. Just do this.
See, it's a perfect sine wave because that's what I wrote into the array. It was a pre-programmed sine wave. That's why it's perfect. But through doing this, you can verify that you can write something into the SD card and then you can read it back. So it's not losing any information from there. Okay, and these are the two demonstrations for two modes for task 2. And for task 3, is about double buffering. So the concept here is that when it's doing a continuous data sampling, like ADCs, like audio amplifier, audio signal input, when you are doing the whistling through the microphone, right? So there's nothing can stop the analog data input. So the thing is, when you are sampling to a temporary buffer on the chip, okay, you don't want to, where it's sampling and filling up the buffers by adding address, right? And you are not trying to write it into the SD card at the same time. It's very difficult to manage. Do you know what I mean? So for example, here's, it's filling up the bucket with water, right? Before it's getting full, you are not supposed to dump the whole bucket of the water to a different place because it's required that you have to dump 512 bytes at the same time. You won't be able to know when it's going to reach that amount of data in there. So it's a better strategy is that when one buffer is doing the sampling or data acquisition, I just like to do it. And after this is done, you use another buffer to do the data acquisition. But at the same time, because this was done previously, and then you directly just throw the whole 512 bytes to the SD card by a simple write operation. Okay, so you need to use flags like being filled or filled, right, to show the status of the buffer. If this is filled, you are not supposed to keep putting data from the data input anymore, right? So you want to stop, and then the blue buffer or the second buffer the status should be being filled. Okay, so whenever it is being filled, it's being used as a data acquisition buffer. And it's called red buffer and blue buffer, but actually there's no difference on the chip. It's just the name of the array, right? There's nothing different. So that's the strategy of it. And for the SD card hardware, a lot of students have questions about it. So first, the SD card has it's a SPI communication, right? And in old times, they have old names and people already abandoned the old names. But now we should use the modern names of the SPI communication, including SDK, SDO, SDI, and CS. All right. So these ones are the names we should use, and abandoned names are MOSI, Missile, SS, and so on and so forth. All right. We call it controller, peripheral, or leader and follower. So in our in-class assignment, we should use leader and follower. So to be consistent with the embedded system class in the spring. So it's gonna be leader and followers, but you still need to know what that means. Some of the chip company didn't update it, right? But That's just the concept over there. And one thing you want to know is sometimes you'll see a different pin name. I'm going to put on the final exam, right? Because it's just so common everywhere. If you see SDA, SCL, and that is for the I2C communication protocol. And if you see mostly missile, SS, SCK, and that's for SPI, but this was the old name, right? So SDI, SDO, CS, SCK. So you can see SCK hasn't been changed. It's a clock. It's a clock. So CS is chip select. Usually it's active low, has a bar on the top. So SDI is the input, SDO is the output. All right. If you for example, this is your follower, and we have a leader here. SDO, SDI, CS, SCK. So for interfacing between the leader and follower, we should do SDO to SDI. That makes sense, right? So the output goes to the input of the follower, and SDO, SDI, right? The follower output goes to the input, leader's input. So you can see it's bidirectional. Okay? And CS, chip select, and clock, ICK. So this hasn't been changed, ICK. For I2C, you can compare I2C and SPI. So this has less number of pins. And you can count, only 2 pins. And this pin is bidirectional, can do either from leader to follower or for the leader, doesn't matter. So this is the clock from the leader. It's sending a clock to the follower, right? So something you need to know. And for example, this is a I2C leader, And for I2C, the good part, since we're not covering any examples on I2C, but you need to know that the I2C can handle multiple devices at the same time. So you can hook up 1, 2. So every single one has a different address. Examples of these I2C followers like OLED, okay, the accelerometer MPU sensor, accelerometer, and many of the modern sensors are using I2C. It's a really popular communication protocol, and the advantage of that is it has less number of pins. And we all know the pin resource on the chip is very expensive. If you can use less number of pins, so you can use other pins for other purposes, right? So I2C has this advantage, and you can hook up a lot of followers to the same bus. Okay, that's the I2C bus. For SPI, you can tell it occupies 4 pins compared to I2C is less ideal. Okay, but this can run faster, right? So several megahertz, let's say. So this one is usually like 40 kHz or something, okay? 100 kHz, like that. Should we use I2C for IC card? Why? Too slow, right? Takes forever to transmit a video file to it. Should we use SPI for long distance transmission? Why? Like a practical example over here. Pagosa Spring hot tubs. All right, there are 25 hot tubs. 25 hot tubs everywhere. All right, and you can plug in a little temperature sensor here, and you are trying to build a little hub data center to process all the temperature sensor data from all the pools. It's about like 30 acres of the property and how to deal with it. So first,
Wouldn't it be because like the data is traveling so far? I forgot the name of it, but it like kind of gets corrupt on its way there.
yeah, so you should use analog temperature sensors or digital temperature sensors. Analog. Analog? Why? Like thermocouples? Yeah, heard about thermocouples? Yeah, thermocouples output voltage to represent the temperature data, right? So the analog voltage, you have a little, it's outputting like 100 millivolts, and there's noise getting into it. It's changing from 100 millivolts to 120 millivolts. So we're getting a wrong data, right? So analog, never using analog for long distance transmission. Long means, longer than a meter, I think. Shouldn't. So we are thinking, hey, if I use a thermocouple here and digitize it, ADC it, right next to it, so I can send digital data out. Good, yeah. But there are commercial off-the-shelf temperature sensors already have everything into the chip, so you don't have to do an amplification and digitization by yourself, right? So it's basically outputting digital data by itself, the little sensor, tiny, and it's directly outputting digital signal, okay? So you want to pick up a SPI port for the digital output, that kind of sensor, or I2C type of output of the temperature sensor. Which one you want to pick up? So the goal is to digitize everything directly or right next to or directly at the pool, right? You don't want to transmit analog signal at all. So whenever the temperature data is acquired, you want to digitize it, convert it to 1 and zeros, so it's more resistant to noises. Okay? Which one you want to use for the rest of the transmission? I2C, because it's slower, right? So the slower you can transmit for longer distance. Why? Because all these wires, they are being wrapped by a rubber material, and there are so many parasitic capacitors are just at the cable. So in that case, if you have a high-speed transmission, it will maybe just go through the capacitors and short them to ground. So eventually they are being canceled, being attenuated. So you are not able to, you know what I'm saying? So whenever you are oscillating a digital signal at a very high speed, that means you are charging and discharging a capacitor really at a high speed as well, right? If you have a large bucket, are you able to charge and discharge it efficiently? If you have an ocean, do you think you can fill it up and pump it out efficiently? No. So the long distance, the cable has a lot of parasitic capacitance, which means you have an ocean, no capacitor, and you don't want to charge and discharge it really fast. You want to slow it down. Okay, so take the time to reach logic 1 and go back to logic 0. So in that case, you want to use a slower communication port. So in this case, I2C is better than SPI. And also temperature data, do you really need a 40 megahertz for the temperature? It's not changing that fast, right? People cannot sense it. So which is fine. So usually we sample the temperature, just one data point, 1 byte, per 2 minutes will be fine. Right, so in that case, we use I2C for that application. Any question on this? So the address on the SD card, like what I'm saying here, the SD card has many pages, but how many? You can calculate it, but there are many pages, and everyone, or it's called page or block. Every block has 512 bytes. So the address of the entire SD card starts from address what for each byte? Address 0. Like an address decoder, right? So decode every single entry on the SD card. So the last one's address is what? 511. Okay. What about the 16 gigabytes SD card?
16 times 10 to the 9 is 511.
2 to the 10 is what? 1024, right? It's 1K, right? Is it a 1K? 2 to the 10th is 1K. Is that 1K? Am I losing anybody? 2 to the 10th is 1024 is 1K, right?
Yeah.
So 2 to the 10th times 2 to the 10th is what? 1 mega. 2 to the 10th times 2 to the 10th times 2 to the 10th is 1 giga. Which is 2 to the what? 30th. Is 1 giga, right? 1 gigabytes. What about 16 gigabytes? 30 something, right? What is that? That's 16 gigabytes, and the SD card I will give to you guys will be the 16 gigabytes SD cards, and so I'm asking what's the very last bytes address.
CE351 minus 1.
You have to write it down in the binary form or hex form. Think about it. So this is 2 to the 34th, right? Every hex byte has how many binary bits? 4. So you're expecting from 0x0 whatever 0 to the very last 0x something, right? And that one has to be, by looking at this one, it has to be OFs, right? OFs at the very beginning at least. So how many Fs at least? 30. Let's do 32 first, right? So 32 will be 8 Fs. 8 Fs will give you 32 ones, and then I need 2 more ones. What that number is?
3. 1
1 is what?
3.
Yeah. Because this guy will be 0, 0, 1, 1, right? Eventually adding to 32 ones or having 34 ones. The reason for that is this little bit, if I got a 1 here, that represents what? What? 34th. So there are 34 ones following that number. So that is why 2 to the 34th minus 1 will be this number. Oh, yeah, this number. Any questions on this? That'll be the last byte. Deep down somewhere on the SD card. Okay. Question number 1, 2, 3, 4 are all answered. Okay, another one. Let's go back to the web page. So we got a leader and follower doing the communication. And you can see the leader will send out the clock. Right? Follower is not supposed to send the clock. So if you take the embedded systems in the spring, you will learn that, okay, so when I'm writing the digital module for the IPGA, right, for the chip, the ISPI controller's module and the follower's module are totally different. Because the controller's module has to do the SDK, the sending out the SDK, and also the chip select as well. So the leader send out the chip select, not the follower. So the leader will start the communication. Okay? Not the follower. If you go to the website of the module here, that's the Skyboard schematic. What are required? What are the modules that are required for the SD card operation? So you can see that SD card is taking 3.3 volts. And you are not supposed to use 5 volts to drive it, including all these SPI communication ports. The SPI, including all these ports, are giving 5 volts logic. It's gonna potentially either reduce the lifespan of the SD card or damage it directly. We don't know yet. But if the SD card is sending out, for example, this one, SDO, right? Oh, one question. What is this guy here? What is this guy? What is this chip?
SD card?
That's the SD card socket, right? You are not soldering an SD card on the board, right? It's a socket. But the thing is, when you plug it in, it makes the connections accordingly, right? But this is a socket. This is a socket. So the socket, which represents the SD card anyway, okay? So the SDO port here of the socket will be the data output of what? Of the microcontroller or the SD card? SD card. Right? That's the SDO, data out. The data output of the socket will be the data output of the SD card. Okay, so the data output going to the microcontroller's input, right? So this guy goes there. So in that case, actually, this pin doesn't matter that much. Why? Because the SD card is not taking in any voltages from my controller. It's sending things out. It's not damaging itself by sending something out. Okay? So whenever the SD card is sending something out, it has to be 0.3 volts logic, 0 and 1s, but the 1s will be 0.3 volts. So the microcontroller takes that in and won't get damaged. But the 3.3 volts will be treated or be seen as recognized as a logic 1 for the microcontroller, because it's higher than 2.5 volts as threshold voltage or switching point for the logic gates. So 3.3 volts as an input to the microcontroller, which is a 5 volts logic, will be recognized as a 1. It's a very practical note here, not just for this application, for all the other things as well. Are you getting that? So if you have a, now let me just draw it on the paper. I've seen this a lot of times. So it doesn't have to be SPI, okay? And this guy has a 5 volts logic. This guy has a 3.3 volts logic. All right. Let's see this is RX and TX instead. Works or not?
No.
No. What kind of change?
You put like a regulator in between two.
Which one?
Like in the middle.
Here, right? You have done this. Have you done this before? If you don't have a level shifter, this will work, right? It's a voltage divider. You can use a, let me see, 2K? No. So the goal is 3.3 volts divided by 5 volts should be equal to, you know, you are not able to find 3.3 k ohms all the time, right? It will be fine if it's very close to that value. So let's just make it ideal over here, right? It's gonna be 3.3 k ohms, and this guy will be 1.7 k ohms. Does that make sense? So the voltage divider is dividing this. Big data is going out from the TX of the leader, right? So here's the 5 volts logic. It's sending a TX, sending voltages out. So sending out is getting divided. So it's 3.3 k ohms divided by 3.3 k plus 1.7 k, which is 5, right? So we are getting 3.3 volts logic for the RX. It's gonna work. I've been doing this a lot of times. But for the top one, you don't have to do anything to it. If you want, you can, but usually we don't have to, right? Because the 3.3 volts and 0 volts, that's going to be the oscillation of the digital signal from this to the leader. It won't affect the data reading here because 3.3 volts will be recognized as a logic 1 and 0 will be recognized as logic 0. So it will be fine, okay? It will be fine. So if you have this kind of situation in your design for the senior project or somewhere else, you know how to deal with it. Similar concept here, I think. So this device is not exactly a level shifter. It's called a buffer. If you search the name exactly on DigiKey, you can see this device is actually called a buffer. So you can see all these OEs. OEs are, I know E is enable. I forgot what O is. Output enable or something. I don't know. Doesn't matter. So usually E represents enable. Okay. And it's active low, which means you need to give a 0 to enable it. So I'm always enabling this buffer. So I'm shorting all the OEs to ground, okay, to ground. So it's always getting enabled. And you can see you have 1, 2, 3, 4 are port A's, and 1, 2, 3, 4 are port Y's. So usually the A ports are inputs and Y ports are outputs. And there's just one power supply. Doesn't like other level shifters. They have a 5 volts here to power up your input and 3.3 volts to power up the output. I mean, it doesn't have any, it's a buffer. Apparently it's a bidirectional buffer. It's only have a 3.3 volts over here. So the thing is, if you have a, let me draw the circuit for you guys. Okay. A buffer could be, I believe the circuit is more complicated than this. They're selling it for money, right? Not like just 2 inverters. Let's just say there's 2 inverters over here. Just in, it could be very representative. So 3.3 volts. Okay, and you have a 5 volts logic here. What the output looks like?
0.3 volt.
Yeah, it's gonna be 0 to 0.3 volts. Right? Doesn't matter if I haven't taken it outside, but I just let you guys know because all the inverters are being powered up by 3.3 volts. It's not able to supply 5 volts. Okay, so 5 volts will be recognized as a 1, right? As the 1 is going to turn on the NMOS and they're going to pull it down. So for 0, it's going to turn on the PMOS, and so it's going to pull out this to 3.3 volts. That's the only supply available to the output. So just imagine that all these are A ports, all these are Y ports of the chip. And so it turns out to be like all the PB ports are the PB, right? P something, PE, PB, PK, whatever the ports are the ports of the microcontroller, right? I've seen the port's name, P something, right? So these are the 5 volts ports. The 5 volts ports are sending signal to the A ports as the input, and output ports are 3.3 volts output logic, and these are shorted to the SD card, which makes sense, right? But there's one exception here, PB3. I think Kai made a mistake over here, but it still works because it doesn't matter. You can see this guy. So just adding to this, right? So adding to this. Because all these ports are bidirectional, so I believe it has this kind of feature there as well. Okay, also 3.3 volts. So if you use this port as an input from the Y, it is also able to send signal out to the A ports. There's only one power supply, which is 3.3 volts. Okay, so in that case, if you're outputting 3.3 volts logic over here, are you going to get 5 volts logic at the output or no? No, so it's going to be 0 to 3.3. Is that ideal? Nope. Will that going to is this going to work? Yes. The 0 to 0.3 is also 0 to 1, right? Being seen from the mega chips side. So now this is clear. This is clear. You could just directly copy and paste this structure to your board, and this is the SD card socket. So 3.3 volts that requires the power supply of the 3.3 volts regulator, and the 3.3 volts regulator's name is LP2985. It's over here. It's taking in a 5 volts power supply and output of 3.3 volts. This is I think the SD card is the only device on the board using 3.3 volts, and nothing else is using that. So this guy is just for the SD card. Could you recognize this chip on the board?
Probably not.
Probably not. Where is that guy? It's here. Okay, it's here. And so the 3.3 volts is this guy, I believe. And you can see you have multiple, have probably 2 chips has the same package, which means they look the same, but they are totally 2 different chips. So which means the packages are being used, can be used for totally different circuits. Just keep that in mind. And what's the name of this guy? It's called ISO-T23-5. So 2-3 means I have 3 pins on one side, 2 pins on another side, and totally 5 pins. So ISO-T surface. You just search for that. Well, Google don't have to. Don't have to guess, right? ISO-T23-5 name. Package name. Small outline transistor, something. All right, so if you see this type of package, you should know that it is ISO-T23-5. It's a really popular package. It's tiny, right? It's pretty good. And this is for the SD card's level shifter or buffer. Why I can tell? Because there's only one chip on the board has that many pins like this, right? So this is 7 pins on each side. No other chips are like that, so you can easily tell this is the level shifter. It's pretty close to the SD card as well. You want to verify if your SD card, because all the code are provided to you guys. So if you upload everything to your board and it's not working, right? Before asking me any questions, what you want to do first? What's the first thing you want to test? What's the first thing you want to test? You want to probe. 3.3 volts power, right? So if you're getting 3.3 volts voltage. If you're getting 3.3 voltage from the regulator, right, but still not working, what you can do? You have to check if the voltage, yeah, you do have 3.3 volts out from the regulator, but if that voltage eventually being delivered to your SD card, right? You have to probe that one. Are you going to directly probe the pad of the 3.3 volts power of the SD card, or the pin of the SD card package socket? Yeah, that's an easy answer. If you just probe the pad and you see the 3.3 volts and still not working, should you just directly complain to me first, or you want to do something else? You don't know if you are getting a good soldering on that, right? So you have because the traces are delivering that voltage to the pad. It doesn't mean that your socket, SD card socket, is able to take that 3.3 volts. If you don't have a good soldering joint on that, there won't be any connection between the pins of the socket and the pad, right? So make sure it's being delivered to the pin of the socket. So know the SD card will be powered up. Okay? And if that's power and then the ground pin, you should do a continuity check. You want to hear the beep. Don't measure the voltage at the ground. I've been talking about this for a lot of times. You are not supposed to probe the ground, and you measured like 0 volts from the multimeter, and you are telling me that the ground is shorted to the common ground. That's wrong, because it could be a floating pin, which is not reading any voltages on it, right? So what you want to do is not reading 0 volts from the ground pin, and you want to test the continuity of it. So just change the channel to the continuity checking of the multimeter, and test that ground and the ground of the common ground of the board, right? To hear the beep. So both power and ground are working, and you think everything is connected correctly. What else you can check? If it's still not working, what else? Do you have the SPI porous pins available on the skyboard to probe? Yes, there are so many pin headers on the board around the chip. There are so many pins. I'm pretty sure the STO pins are available somewhere. So you can directly hook it up to the oscilloscope and look at the signal, see if it's actually sending signal to it, right? If not, it could be something wrong. I mean, always check the soldering first, right? It could be something other things can go wrong as well. And let's see if we are covering all the questions over here. Okay, another thing. You may have searched online for SD card libraries, and the very popular library has the header files, and the name of the header files are SDH, ST.h, and SPI.h. And these examples require you to open up a file. So it's actually using the Windows file systems. So it's basically opening up a file and put on the SD card first, and open up the file and then log data to the file. And then close the file, right? When it's reading it, it opens out the file and read it and then close it. So we're not trying to do that. We're not using the file system to write and read the data to and from the SD card. The main reason for that is it's just super slow. We don't want to rely on any of the APIs or the libraries to do all the block writing and reading. So we want to you guys are computer engineers. You can directly touch the very bottom level of the protocol. So we're actually writing and reading block by block by ourselves. Okay, so that will be way faster. If you have a senior project or something doing continuous data acquisition, you never want to use the files, whatever, open, close, whatever, all these kind of things. You want to use a different library, and the library's name is SDFAT. SDFAT. Can't see it somewhere, but I do have the tutorial. Oh, it's over here. This one, right? So if you don't have it, search. Just follow this instruction over here and search for it, and then install it to Arduino IDE, and then include it into your code. You should be able to use it after that. Okay. So the task 2. So task 1 is basically just to install the SDFAT into it, and then you use example code which is given. Did I post it here? Not yet. I'm gonna do it. So that's example code is given. Task 2 is also given. You can directly upload it to the Skyboard and then run it. And for task 3, that's for double buffering, data acquisition. And I only left several areas blank for you guys. Really simple. So you want to set up the stats, the state for the buffer. It could be being filled, you know, these two different states. You want to understand the code and see which one you should use for these places. Okay. So the way to play with this one is, you can read the video after the lecture. So you whistle, right? You whistle, and then it records the data and save it onto the SD card. And afterwards, you read it from the SD card and save it to the file in your laptop or desktop. I think I already answered all the questions on the sheet, right? Anything I'm missing here? Not really, right? Okay, perfect. That's it for today. And Wednesday, I'm gonna post another video on the playback. Couldn't finish everything today, but you know, it involves a low pass filter and a lot of really interesting stuff you need to learn. Okay, you need to know. All right.
Is it